All right, AP Physics Unit 4 Linear Momentum Ultimate Guide. Yeah, pretty exciting stuff. Momentum, it's a pretty cool unit. It's really good for collisions and explosions and relates motion in that way because we can use conservation of momentum, which is similar to how you use conservation of energy, which is really nice. But this is used for a little bit different things. These are the four sub-units of Unit 4. We got linear momentum, where we'll just talk about introducing momentum and what it is, and then we'll talk about what change in momentum is, which is impulse, and then we'll cover conservation of linear momentum and how we can apply that to collisions and the difference between the different type of collisions. So the timestamps will all be down in the description, so feel free to jump around as you need, and happy learning. So the momentum of an object, or linear momentum, is the mass times its velocity, and that's when it's moving in a straight line. So the units of momentum are, we have the kilogram from the mass and we have meters per second from the velocity. So this unit will be a kilogram meter per second. And so this momentum is going to be a vector because we have a vector as velocity and a scalar which just doesn't affect the vector's direction, so we'll have a vector for the momentum. And so momentum can be a really powerful tool in physics to solve problems, and they mainly are used to solve collisions where, let's say we have like something colliding with each other and we want to know the final and initial momentums, or in like an explosion where you have like some ball or something and it explodes into pieces and you can compare each piece's momentum. So this will be just a simple introduction to momentum, so let's do a couple examples to see how we use it. Okay. So let's compare the momentum of a 0.0006 kilogram bullet traveling at this speed, which is about 2,000 miles per hour, versus the momentum of a 1,000 kilogram car traveling at about 1 miles per hour. So if we go ahead and calculate this momentum, we know it's just the mass times the velocity. So if we plug these in, times the velocity, which is 894, okay, we're going to get 0.054 kilograms meters per second. And if we compare this momentum, which is still mass times velocity, we have 1,000 kilograms here, traveling at this 1 mile per hour speed, or 0.44 meters per second, we get 440 kilograms meters per second. So that shows how, even though this bullet is traveling way faster than the car's momentum is magnitudes larger than the bullet. And that makes sense because if we have a car, let's say we have a big car, right? And it's traveling with some velocity, and you shoot like a little bullet at it. Shooting this bullet at the car is not going to cause the car to change its velocity that much. And we'll learn later that this force that it applies depends on relating these changes in momentum. So let's consider the Newton's second law, F net equals the mass times acceleration, right? We can rewrite this as the mass times what the acceleration equals, which is the change in velocity over the change in time. But you might notice here we have the mass times the change in velocity, which we know that we just learned that momentum is mass times velocity, so the change in momentum will be the mass times the change in velocity. So we can plug in momentum here, and we get that the force net is equal to the change in momentum over the change in time. Okay, so that's one big equation that we'll use. And so now that we have this force equals the change in momentum over the change in time, if we multiply both sides by change in time, we get the force times the change in time equals this change in momentum. And what we call this, we can also say P final minus P initial, but what we call this change in momentum is we call it impulse. And so we'll say that the force times the change in time is equal to the impulse, which we'll denote as a J, which equals the change in momentum. So that is the other big equation, which is really saying pretty much the same thing as this, just giving this term a name. And so the impulse, the impulse j is going to have the same units as momentum, but when you first look at it, you might think, okay, we have a Newton and a second, so you may see impulse units described as a Newton second, but if we break up what a Newton is, kilograms meters per second squared times a second, these end up canceling and we get a kilogram meter per second, which is the same units as we had for momentum. So this impulse is also going to be a vector quantity, and it's going to be in the same direction as this net force, since this time is not going to change the direction. Okay, so let's look at a couple graphs relating using these equations. So let's say we were given a graph of the momentum versus time. Since we know that the force equals the change in momentum over the change in time, this is just a rate of change right here. This is just a rate of change right here. So if we have a graph of this, the rate of change is just a slope. So if we wanted to find the force given these two variables, we could find it by just using the slope here. So this would be whatever the slope is, would be F net. And like right here, F net would equal 0. And right here it would be whatever the slope of this line is F net. So that's how you could use the momentum and time to find the net force. And let's say we're given a net force versus time, or a force versus time. Since we know that impulse is just the force times the change in time, now we're multiplying these two together, which means that's going to give us the area. So if we're able to find the area of this, we can find what the impulse is. And so this graph is pretty common to see if you have if you're hitting like a baseball, for example. You'll have a short amount of time where you're applying a force, and if you find but your force won't be perfectly even throughout. But you might see this graph approximated as something like, you can either approximate it by finding the midpoint and taking the area like this, or you may even be given a graph that looks something like this, and you can find the area just using geometry. So that's something to be aware of for the graphs that relate to these equations. Alright, so let's do an example here using impulse and change in momentum. So we have Bob pitches a 0.5 kilogram baseball to Bill. Bill hits the ball straight back at Bob with a force of 1,500 newtons. The ball was in contact with the bat for 0.01 seconds and has a velocity of 22 meters per second when it leaves the bat. What was the speed of the pitch? Okay. So let's write out what we know. So we know the mass of the ball, which is 0.5 kilograms. We know the force, which is 1,500 newtons. We know the time, or the change in time that it was in contact with the bat, was 0.01 seconds. And we know the final velocity of the ball, which equals 22 meters per second. So let's draw a little picture here. So we have the pitcher, which is Bob. And then we have the batter, which is Bill. So Bob is going to throw this ball at Bill, right? So we have the ball here, and this is the V initial right before it hits the bat, and that's what we're trying to solve for. So that's our question mark. But Bob is going to hit this ball and going to send it straight back at them with a V final, straight back at Bob. So, and this force must also be in this direction because it's hitting the ball in the opposite direction. So now we need to define our directions here. So we'll call this direction the negative direction and this direction the positive direction, because it's going to depend on where we have our momentums. So the direction does matter, and your sign will matter because we're dealing with vectors. So now, since this pitch is coming in the positive direction, the final velocity, since it comes in the opposite direction, is going to be negative. So we can denote this final velocity as negative, but the force is also in that direction, so the force will also need to be negative. Okay, so now we can set up our equation to see if we have enough information to solve this. So we know the force times the change in time is equal to the change in momentum. And the change in momentum equals the mass times velocity final minus velocity initial, or change in velocity. So we have force, we have time, we have the mass, and we have the v final, so we have everything to solve for the v initial velocity. So we can go ahead and divide by the mass, and then rearrange the equation for velocity initial, and we will get the v final minus this force change in time over m. And if we just go ahead and plug in all the values we have, we can solve for the velocity initial of the pitch. So that'll be right before it hits the bat. And so if we go ahead and plug those in, we get an initial velocity equal to 8 meters per second. And that'll be positive since we denoted that direction of the pitch to be positive. So that's our initial velocity, and that'll be our answer. Conservation of momentum is pretty much why we use momentum in physics. You know, when you think about different physics quantities, you can really multiply any variables together and call it something. But the reason we multiply mass and velocity together to get momentum is because momentum is significant, and the main use is when it's conserved. And so let's talk about what that means. So conservation of momentum basically means the momentum's not changing in the system. So our momentum initial equals our momentum final. Or you might see the change in momentum equal to 0. And that's that total momentum of the system. So if we have multiple objects in the system, then their net momentum is going to be different. So if we have this initial momentum equals the final, we could also write it out as the initial, like the separate masses, the separate mass times velocity initials, right, equal the final of each one added up together. But it doesn't mean that each object's momentum is going to be exactly the same. It just means when you add them, they equal each other. So let's talk about when can we actually use the conservation momentum. So let's say we have like the ground, and I'm going to make the ground a little bit lower. Let's say we have the ground and some ball, right? And the ball is falling downwards, the velocity. In this case, if we take the system to be the ball, we cannot use conservation momentum because there's a net force acting on this ball, and it's the force due to gravity. But if we have this same exact situation with a ball falling down to the ground, but now we take our system as the ball plus earth system, like that, then this force due to gravity is within the system, and there's no net force, so then momentum of the system is going to be conserved. And so we'll see how this can be used, and the main thing that you'll see momentum being used for will be collisions and explosions. So if you have like, you know, two boxes moving at each other and they collide and they bounce off or they stick together, you can use conservation momentum. Whereas like energy deals a lot with like changing in heights with speeds, momentum does a lot with interactions between objects. And when you have them in the same system, their total momentum is conserved. That's why we use this. So let's look at an example of this conservation of momentum. So we have a block of mass m slides at the constant velocity of 15 meters per second. The box then explodes into two pieces. One piece has 1/4 the mass and slides at 20 meters per second in the same direction as the initial block. What is the velocity of the other piece? Okay, so let's draw what we have, right? We have a box right here, and it's moving with some velocity initial, and that'll be 15 meters per second. And so when it's sliding, it then breaks off into two pieces. And so one piece moves in the same direction as v final 1, we'll just call it, and this has 1/4 the mass. And so the other piece must have 3/4 the mass. But we don't know what this velocity is. The velocity final 2 is what we want to figure out. But we know what the initial system was. So the system is going to be the block in this case. And since it's sliding at a constant velocity, we can assume there's no frictional forces, because otherwise it would be slowing down, or you would have to also have an applied force. But since it's moving at a constant velocity, there's no net force. So that's why we know we can use conservation of momentum in this situation. Okay, so let's write out our variables so we have them. So the mass initial is just m, because before it breaks, it's just going to have a mass of m. That's what it says right here, mass of m. And then we have an initial velocity is 15 meters per second. Then we have our m1 final, which equals 1/4 the m. We have our m2 final, which is 3/4 m because it's just the whole other part of the box. Then we have a velocity 1 final, which we know is 20 meters per second, and the velocity of the second piece is what we want to find. Okay, so one more thing we need to be careful of is this momentum is a vector, so we do care about the direction of this box. So we can denote this right motion as positive, and so the opposite direction will be negative. So the initial velocity is going to be in the positive direction, and we know since the second piece is coming off in the positive direction, it's also going to be in the positive direction. So both of these velocities will be positive. And then if we get a final answer that's negative, we just know it's moving in the opposite direction. And if it's positive, it's moving in this rightward direction, or the same direction as the initial block. Okay, so now we have to find the velocity of the other piece. So we know we can use conservation of momentum since it's a constant velocity, no net force. So P initial equals P final. And so we can now get all our pieces of momentum. So the initial one is just M naught V naught equals the M1 final, V1 final, plus M2 final, V2 final. And so now we have all these variables except for V2 final. So we can go ahead and rearrange this equation. But first, actually, we can actually plug in what we have here. Since we're not, for the masses, we can go ahead and plug them in. And so our M naught we know is just M, and V naught, I won't plug in the numbers yet. M1 final is 1/4 M, V1 final, and M2 final we know is just 3/4 M, V2 final. And so now the reason I did that is because these masses are going to cancel because they're all relative to the same mass. And so we can now just get this in terms of velocities. And now we can rearrange it for V2 final. And you could rearrange it first and then plug everything in, the masses would divide out, but this just simplifies the equation a little bit. So now we can rearrange it. 3/4 V2 final equals V naught minus 1/4 V1 final. And if we go ahead and plug the rest of these in, or rearrange the fraction, we'll get 4/3 V naught minus 1/3 V1 final. Okay, and now we have all these values, so we can go ahead and solve for this and say V2 final equals 4/3 V naught, which is 15, minus 1/3 V final, which is 20. And so this gives us a value of 13.3 meters per second. And so now we know the other piece will be moving at this velocity, and since it's positive, it'll also be moving in the same direction as the initial block. So if we think about this, the block is moving forward, it breaks, and now these both still move forward, but this one's going to move slower than the original block, and this one's going to move faster. And the reason is because the system's center of mass velocity is not going to change. And so let's talk about what that means right now. So center of mass velocity is just the sum of the momentum divided by the sum of the masses, which we can break up into the mass times velocity and summing those with the total mass. And so we can actually get this just by using conservation of momentum, because we know that if the P naught and P initial equals P final, if we know that the P initial is the sum of the momentums initially, and the final is just, let's say we have like multiple pieces and they come to one blob as moving as a V final. Now we have the total mass times the V center of mass because it's just one velocity, and we can divide by this M, and we get the sum of the momentums over the mass. And so when momentum is conserved, so is the velocity center of mass. And so let's go back to that initial equation here, or this initial problem, And let's solve for the velocity center mass using our our final velocities and see why this matters. So we know that the velocity center mass initially, let's do this in a different color. We know the velocity center mass initially, there's only one piece initially. There's only this initial block. So it's going to be 15 meters per second because it's just the velocity of that block. And then, so that's initial. But now our final velocity, we have to use our equation. So our final center mass velocity, since we have multiple pieces, we have to do the sum of the mass times velocities over the mass. And we could still do the sum of the mass times the velocities over the mass, but since there's only one piece, the masses are going to cancel and we just get that center of mass velocity right there. So when there's one piece, you can just pull it straight out, but even if you use that equation, the masses just cancel. But in this case, there's multiple masses multiplied by different velocities, so that's why we have to use this. So we can break this up into each piece. So we have the 1/4 m v1 plus the 3/4 m v2 divided by the total m, which is just going to be m. And so now these masses end up canceling, and we can plug in the values we solved for. And if we did the first question correctly, we should get the same velocity. So this one's 20 plus the 3/4, and this is what we solved for, the 13.33. And this is just over 1 since the masses got canceled. And when you plug this into your calculator, you'll get 15 meters per second, which is the same velocity as initially. So this velocity center of mass did not change. And so that's whenever the momentum is conserved, so is the velocity of the center of mass. And so that center of mass velocity doesn't change when the momentum is conserved. So let's talk about the two main types of collisions. So first we have elastic collisions. In an elastic collision, the energy is conserved. So we have the kinetic energy, the change in kinetic energy will be equal to 0. So what will that look like? Let's say we have a ball traveling at each other. Let's moving some initial velocity. Let's say they're both moving the same velocity. After they collide and bounce off each other, they will still have that same initial velocity. So the velocity is conserved, and since velocity is within the energy will be conserved. And then also during this collision, the momentum will also be conserved, so the change in momentum will equal 0 as well. Now let's contrast that to an inelastic collision. So an inelastic collision, the kinetic energy is not conserved. It does not equal 0. So if we look at a situation where that is, let's say two balls are moving at each other. Let's say one has a v1, one has a v2. And after they collide, they're moving at different velocities, right? We'll say 3 and 4. But they're going to be less velocity than initially, which means some energy has dissipated. And so energy cannot be created or destroyed, but it can be transferred. So it may be transferred to sound or heat or some other energy source, but the kinetic energy will not be conserved. And so if we have a collision where two objects are traveling at each other, and after they collide, they stick together and either have no velocity or some velocity, we call that a perfectly inelastic collision. But even with this collision, the momentum is still going to be conserved. So the change in momentum will still equal 0. Alright, let's look at an example where we apply these momentum and energy principles to a collision. So we have a ball at 25 kilogram ball traveling to the right at 10 meters per second collides with a 50 kilogram ball traveling to the left at 5 meters per second. If the first ball travels at 3 meters per second to the left after the collision, what is the velocity of the second ball? Okay. So let's first write out what we have. So we have the mass, and we'll call this ball 1, and we'll call this ball 2, just for our subscripts. So the mass 1 is 25 kilograms, and it's moving to the right at 10 meters per second, so the velocity initial is 10 meters per second. And so the direction does matter here, so we'll denote the right as positive, which is typical, and the left as negative. Okay, so then M2 is the mass of the second ball, which is 50 kilograms. and it's traveling to the left at 5 meters per second. So v2 initial is going to be 5 meters per second, but since it's to the left, we'll note this as a negative velocity. Okay, and then the first ball travels at 30 meters per second to the left after the collision. So we know that the velocity of one final is going to be 3 meters per second, but it's to the left, so that's also going to be negative. And we want to know what is the velocity final of the second ball. Okay, so when you're thinking about this, should we use momentum or should we use energy or something else? Well, we know that momentum is always conserved, and it doesn't tell us if this collision was elastic or inelastic. So it's always safe to use momentum when you have a collision problem like this. And since these velocities are constant, we can use that conservation of momentum. So we know that the momentum of the system initially will equal the momentum of the system final. And we'll define our system as the two balls. Okay? So we can write out our two momentums. So we have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. And it's very important to be clear about your subscripts because there's going to be a lot of different variables you're working with when you have a lot of different objects. So just make sure you're clear on objects 1, 2, 3, however many you have, and the initial and final for when things are changing. In this case, the mass is not changing, so we don't have to worry about having initial and final masses, but if they did change, you would want to worry about that. Okay, so we want to solve for v2 final, so this is what we want to solve for. So let's rearrange the equation to get that by itself. So we can say m2 v2 final equals m1 v1 initial plus m2 v2 initial minus m1 v1 final. Okay, and now all we have to do is divide by the mass, and we can get this equation with v2 final on its own. All of this over m2. Okay, so now we can just plug in our values and get this velocity too. So m1, which is 25, v1, which is 10, plus m2, which is 50, v2 initial, which is negative 5, because the direction does matter here, m1, which is 25, and v1 final, which is negative 3, all over m2. Want to be clear about which one it is. m2, which is 50. And so if we go ahead and plug all this in, we'll get a v2 final equal to 1.5 meters per second. And since it's positive, that means it's to the right, because we defined the right direction as positive. Okay, so I'll go ahead and box my answer here. But now you may be thinking, how do we know if this was elastic or inelastic? Well, we're actually able to check that, and that's what the next one is asking this. Was this collision elastic or inelastic? So, how can we tell? Well, we know if it's perfectly elastic, then the kinetic energy is going to be conserved. So we can actually check, does the kinetic energy change from initial to final? So let's go ahead and calculate the initial and final kinetic energies. So kinetic energy initial is equal to, obviously, the kinetic energy of ball 1 plus the kinetic energy of ball 2, which equals 1/2 m1 v0 1 squared plus 1/2 m2 v0 2 squared. And so we can go ahead and plug these in now. m1, which is 25, v0 1, which is 10, okay, m2, which is 50, v0 2, which is negative 5. And so notice that in this case we don't care about directions because the energy is a scalar quantity, and since it's a square, the direction will not affect it. So when we plug these in, we get initial kinetic energy of 1875 kilojoules. Okay, and let's do the same thing with final. So the K final will just equal the kinetic energy final of each ball. So we'll have the same beginning, but this V, we want the final for V1 and the final for V2. Okay, V final 2. Okay. Okay, so we can go ahead and plug in our values here. So we have M1 is 25, the V final one, which is a -3 squared plus 1/2. This is 50, and our V final 2, which is 1.5. That's what we calculated. And we get that this energy is only 168.8 about kilojoules. So this energy, energy initial, does not equal the energy final, because we had 1875 does not equal 169 about. So we know that this must be an inelastic collision because this energy, or the kinetic energy, was not conserved. Alright, thanks for watching this video. Hopefully it was helpful. Feel free to go back and rewatch any sections that you need. Leave your questions in the comments, and see you in the next one.